exercise homework. Today you can do, but I know you prepare the exam, but I give the time, the due date, so the due date is after the next Saturday, so I think after that you can work on that. Just assign and then give you time. Chapter 1, B, A, D, N. I will post down here announced here. Due is September 20th. Right, so your last one is September 17th, right? I remember. Okay. Then I'm going to post on Blackboard, so you have details. Which page number you can find this. You have them. Everybody has this one, right? Yeah. If not, you just refer some others, because different version, the problem is slightly different. This is third edition. Okay. Okay. Next. And brief review, we will start from the end of last class. The principle. We have, if you remember, partial drag here, the kinetic energy, and with respect to the generalized speed, velocity, which is equal to G from 1 to number of n, lower n is number of degree of freedom. And then here, the Qj is generalized, the J's components of a generalized force. So here the definition, n particle, the applied force, right? Only the applied force, since the force due to the constraint already observed into the equation of a constraint. Right. Partial R, partial Kg. Okay, I think that is almost, and we discussed the if the general force, applied force are conserved force, so that is a good problem. So if, let's say first, the applied force, as particle, the net applied force include the external, net external, plus the internal, right? So internal G naught equal to I G I. Here, you usually, if we have several, but let's consider all the internal is for i's particle, all the other J exert on X, right? So here, if they apply the force is conservative, right? Conservative. This conservative we discussed, there are two cases, right? One is external conservative. Plus internal. Here, I just use index since we know the internal is GI something, right? I just want to make this all together. So do not write down this summation conservative. Okay, then we have the external conservative for each part, i's particle is correspond to the external potential and, my negative gradient of external potential, and for the in, many notation here for conservative. And for this internal, it is conservative. That is negative. G already derived out of the partial I, this Vij, partial Ij is Ij. It is said by strong law of action reaction. So those are. Then we have this. So we substitute this. Okay. Substitute this here. Right? Here, then we can have the general force is finally is this only the partial, very simple, the total potential, right? So partial V, partial QG, and V is the total external potential plus total internal potential. So if in details, total external potential for each, the external potential at each particle, and total internal, we know that is this expression, I from 1 to n, G naught equal to I, G or G. I think that is the end of last class. So we keep continuing this class today. We are going to introduce Lagrange, and we are going to introduce Lagrange equation. Then discuss this significance of this. Okay, so now let's keep going. Let's follow this. Still a concern about conservative. It's non-conservative. We are going to after that we're going to discuss, right? So now let's consider. If this case, now we substitute this Qj into this formula, so we have d dt partial t partial Qj dot minus partial t partial Qj equal to Qj, right? Equal to negative partial V partial Qj. Or I move this term to the right hand side, so it became plus, right? Then that is have partial t partial Qj dot partial now, because these are all partial Qj, so I put together. Right? This move here is positive, but I have negative outside, so I have a minus again. Right? So up to here, it almost you can see something here appear, right? But now this one not. So now we are going to discuss if the potential, total potential, is function of only the general coordinate and maybe time. So that means independent of Qj dot. If that's the case, and in most cases we know, right? Like rotational potential, Coulomb potential, those are only depend on the coordinates. Does not depend on velocity, right? And the depend on velocity is magnetic potential, right? Correspond to magnetic field. So in this case, then you can see partial V, partial Qj dot, how much? 0. Yes, does not depend on this one, right? So then we are going to, so that means 0, I add here is 0, still 0, right? So here, let's see, partial t minus v, partial Qj dot is equal to partial t, partial Qj dot, right? Because partial v, partial Qj dot is 0. So now I can add this term. Then we have, finally we have d partial t minus v partial qg dot minus partial t minus v partial qg equal to 0. This is a case for conservative, so now the conditions here, right? That is condition. So that formula is for this condition, okay? Now, with this, you almost see, but I will not give a conclusion so far. So that is the first, if the potential is only a function of general coordinates and maybe time, implicitly or explicitly depend on time. But second one, we are going to extend in general, like a magnetic field. Magnetic field corresponds to magnetic potential. That is, if we have a u. Now, it distinguished v, usually v is only function of coordinates. Now, if you consider extend in general, so we are going to use u as a potential which depends on the generalized coordinate and generalized the velocity and maybe time. So now I include in general. So how about this case? So in this case, the generalized force here we define as this is d dt partial u partial qg dot minus partial u partial qg. That is defined. And it is have the same. You see here. Remember, the general force. The dimension is work, right? In joule. And so because the force in Newton, this is a meter, and depend on this one. Depend on this, will give us either force, torque, but whatever it gives us is joule, right? And you can see here, the same thing. So here, this is energy, and then energy with, this is a meter time, right? And time cancel, so that is meter. This is energy meter, so that again gives us joule. Sorry, the work done, right? This is potential energy. Yeah, work is I think, partial, yes. Generalize the force. Okay, so now we introduce then. Let's submit here. So we have a d dt is start from here. Now d dt partial t partial qg dot minus partial t partial qg equal to, so right hand side is d dt partial u partial qg dot minus partial u partial qg. So I'm going to see this very symmetric, right? So move to the left hand side. All the right hand side move to the left hand side. So now we have totally partial t minus u partial qg dot minus partial t minus u partial qg equal to 0. How many equations? Equations. So now we have a new quantity, which is t minus u. And this equation is for this one. So now we introduce the Lagrange. Here, now we can introduce Lagrange. Okay. Then so far, at the beginning of the chapter, as I said, that we are going to transfer from Newtonian mechanics to the analytic mechanics. That analytic mechanics, we are going to deal with this Lagrange equation and Lagrange equation of motion. So the Lagrange will come from. Now we apply the Albert principle that focuses on this work done, the virtual work, and then we get rid of the constraint part, right? Then by step, so now we found this is the equation of motion come to here, right? Remember, this one is from this applied the force if at the equilibrium dot with delta r, which is the motion work. From that, we finally come to here. So now, we introduce this. Okay, introduce this. So now, first let's see the feature, right? So now, some of notes I want to emphasize here. So this is L is the difference between between T and U, right? Between the kinetic energy and so here is minus. This is what I mentioned. Be careful. It's not like energy. Energy we know the kinetic energy plus potential energy, but Lagrange is minus. That gives us difference. So that is first we need to know. This is also characterize the physical. This does not mathematical formula here, but the quantity physical. Quantity. Which quantities? Kinetic energy here, which is defined for n particles, and from y to n, mi, let's use r, we do not get rid of b, ri dot square. Right, so that is a real kinetic energy, that's not mathematically some formula kinetic energy. And the potential energy here, let me just use V and later the U is in general. So the V we know that is external potential. Sum of all the particle has external potential and plus the internal, right? I G not equal to I E I G. So that is potential energy. And what does mean is this is a real kinetic energy and potential energy. In the later, you will see when we replace the coordinates Ri or Ri dot by the general coordinates, that's different formula expression, but it is represented energy, kinetic energy and potential energy. So first, when you want to write the Lagrange, you need to find the kinetic energy of a system, potential energy for a system. That is the characterize the physical meaning. So that is very important. Number 3, this is a function, so even though it's equal to T minus U, right? T is a function Ri dot, U usually function Ri, or maybe we have Ri dot. But we are, if you look here, it is variable of Qg and Qg dot. That is generally coordinate. So this is initial, you have the physics, but as the coordinates is a function of general coordinates. So that is okay, function of, I just speak, right? And write down so you can understand what it means. So, that means, so we have introduced Lagrange, but that is a function of general coordinate, general velocity. Number 4. So this expression of L, so that expression may be some of the expression like sinusoidal function, some of the exponential for same system, right? So here, for same system, the kinetic energy, potential energy is given, but you can select different type of the general coordinates. So the expression of Lagrange may change, depending on the choice of the, depends on the choice of which type of general coordinates you are going to select. That makes sense, right? So you don't need worry, okay, we have several students here, so I give you a system, like for example, single particle, you may select the spherical coordinates, you may select the Cartesian coordinates, right? So your expression for Lagrange is different, fine, but your kinetic energy potential energy write correctly, then the value. So because this expresses the difference of kinetic energy and potential energy, right? So its value is independent of choice. Independent of. So yes, expression different, but the physical characterized physical quantity, right? That's value independent. So that is the first discussion about this Lagrangian we introduced. And then, so that is introduced Lagrangian. Now we have this equation of, did I already write down? Not yet, right? So now we are going to Lagrangian's equation of motion. Since we introduced L is T minus U, so this one is became, this is partial L, partial QJ dot. After partial L, partial QJ dot, be careful, this is the total time duty. Okay, minus partial L, partial QJ equal to 0. So that, this is the Lagrange equation, and be careful, here we discuss is all the forces are conserved forces. So for all the forces are conserved forces, this is equation to deal with the motion, or to solve the motion, the equation of motion, and get a solution like Newton's second law. So with this solution, the solutions of this Lagrange equation, what is solution? We will have Qj is a function of time, right? This is our solutions by solving this. How many j from 1 to n? And then, but this is not the goal. Our goal is the real position, right? That is, okay. R is a function of Q j dot Qj, right? Qj t. Qj which obtain the solution from the Lagrange equation, and that is our final goal, right? I from 1 to n particles. So from here to here, remember how to get transformation equation, right? We selected a side of general coordinates, and then we found the relation between general coordinates and this real position. That is transformation equation we introduced last time, right? So once we get solution, we are going to get this. Then that is the final solution. That means if from Newtonian mechanics we are going to analyze the force and then to solve the second order, the second order derivative of R is acceleration and solve that. But here we are going to solve this equation with general coordinates, and finally we are going to from the solution convert to the final solution. Right? That is how to apply this Lagrange equation. And now let's go to extend to non-conserved force. Then we discuss in general the feature of the Lagrange and Lagrange equation. So now this is here. And now let's see if the general force, okay, let's say if the applied force include both for ith particle, include a conserved force and non-conserved force, okay? The conserved force we already discussed include external and internal and plus now 70. Okay, so now we consider another group, right? The rest of the other forces are all non-conservative. Then this general force, by definition we know that is summation for all the particles. Applied force partial Ri, partial Qj. So now we have two terms. Substitute the applied force by this, separate into conservative and non-conservative. So we have first one is conservative which we already discussed, we have this result. And then non-conservative. Okay. So for the conservative force, we already obtained that is partial potential, partial QG negative, right? That we just discussed before. Now the remaining part, I'm going to use QG prime. So QG prime is all the general force. QG prime is defined this non-conservative, all the non-conservative come together. We do not know how to do that because this non-conservative force depends on different type of the non-conservative force, the formula. So different type, then the result is different. Not like the potential, like the conservative force, all the gradient, negative gradient of potential, right? So we can get this same formula. But for this one, now, then if this case, now substitute it into this Lagrange equation, if I just direct, okay, here. So we got again partial TU, we observed this conservative force to general force to the right hand side. So we have this minus partial T minus U partial J. Now the remaining part is non-conservative at the right hand side, right? Or that is even, again, it does not affect our choice of the Lagrangian. So the Lagrangian still defined as difference of kinetic energy and potential energy. So left hand side, same as before, but if we have such non-conservative force, we are going to have the right hand side is non-zero. That is the general, we call the general Lagrange equation. Equation of motion. Let's do one example. For the non-conservative force, there's one type of the non-conservative force which still can be expressed in terms of the introduced dissipation function. So now let's consider the example, the fractional force, right? Fractional force. Fractional force, like we have the drop and falling down. So in the air, if you consider the resistance due to the air's particle, so we have a drag force. The drag force is proportional to the velocity, right? So those are the fractional force, which is like this. We use F to distinguish this. This is say that the force with the fractional S particle, S components, that usually is minus, we have a coefficient K, X, and Vx, Vix, right? This is the coefficient. This is the velocity of particle. So this force is proportional to the velocity, negative proportional to the velocity. This is the force. Now for this force, how to write this one? We are going to introduce. We found this force has a relation with the velocity. So we introduce a function which is the square of velocity, then we can see that is nothing but partial derivative. So introduce this equation function. We use capital F and children. So use this annotation. This is introduced is like this. is a function of some or all the particle, even n particle. Each particle has the fractional force applied to each particle along this direction, x direction, y direction, z direction, right? So we have coefficient along x is maybe different, y, z may be different, so we have a coefficient index kx, and vi x squared plus ky, vi y squared plus kz, vi z. This is definition of this dissipation function. So you can see here, this is a function of velocity, sum of O, the whole system, sum of together. Then you can see here, the f, the s particle, okay, if this vector, this is x components, right, is nothing but negative partial, the dissipation function with respect to velocity as velocity vector, or negative gradient, but this gradient is with respect to the velocity, not with respect to the position. Okay. For i's part, so then i's means if there's one of them, right? Half of the kx vi x squared, ky vi s squared, kz vi z squared. That is f q to I. That is dissipation function for a single particle, one of particles. Then the force, just do derivative, right? You can see if you do the derivative, 2 cancel, and then you have nothing but this one, but negative sign, right? So that is very like potential, but here it is a velocity function. So once we have this, now we know this expression of the friction force like this. So friction force is a non-conserved force, right? Not like this. In this case, what is Qg prime? So the Qg prime, by definition, is I from 1 to n, a non-conserved force. Let me just directly use this one, since here is considered I partial Qg, right? Here. This is a force, non-conserved force, if you only consider the friction force. So net is, again, is only that one. That is F, capital F vector, and the index F is the fractional force as particle, right? In the product, that is this definition here. Then we substitute this into here, you will see I from 1 to n, and negative gradient, right? So how to go to next? Now, let's keep the next sign outside, next sign, and then I from 1 to n. The gradient is partial f partial v I vector, right? Is an inner product. Okay, here. This R is not I dot. I dot is vi, right? So here, okay, I think I immediately use, since vi is I dot, right? Since we are doing I dot, right? Velocity. And here, if you remember, when we derive, let me just write the result and give you a brief. Partial I dot, partial Q dot. Remember this? This term, they are equal, right? Remember we discussed, we say Ri is a function of Qj, Qi, and then dri dt, total time derivative, is a function of Qj and Qj dot. Then the partial Ri dot partial Qj dot is equal to this, right? Just remember this. That's why I mentioned this is a very important relation here. So now this is I dot is velocity, right? So now you can see here. So it is negative. Okay. Partial partial QG dot, because it's summation I, right? Summation I does not depend on G from 1 to n. And this is nothing but the total, right? Okay, now here. Each one is half of this, right? But for given index, half of kx with x squared, ky with I squared, pz with I squared is f to the I, as particle the dissipation function. And sum of all I from 1 to n, the total. So here, this is individual, right? Fi total. So now sum over is nothing but minus total dissipation function with respect to QG dot. That is QG, capital QG prime. And with this, now we can come back to here in general now. Is here, right? Now we substitute this QG prime here. Then we have the formula is the Lagrange equation for the system with the conserved force and the non-conserved force, only the fractional force is related to this dissipation function. So the Lagrange equation is this. The right hand side is not zero, right? Or in most cases, we just move to the right hand side. So totally, another expression for the Lagrange equation, we have the dissipation function plus partial f. Again, we have how many equations? We have an equation. This is in case if we have this dissipation function. Okay, the significance of the dissipation function, the textbook has a proof, so to save time, I want to just explain. You can see here the force, this the fractional force is this gradient of this one, right? And work done by the system against the fractional force is F, is this one inner product with delta R. And you will see that is give you this the work done by. I just give you the result. I think then you can. That is characterize the rate of the work done by the system, or the system lost energy to against this fractional force. So here, if your significant is you consider the S particle, right? So that is F, the fractional force in the product of E R dot, and then you substitute this one. Okay, so that is fractional force is negative K F in the V I use vector because that is X component, Y components, and Z components, right? So here, then this dr, I can use dri dt and dt, right? So this one is again is vi. Right? So you can see that is negative of kf vi squared dt, which is that is the negative twice of the dissipation function S particle dt. So here, then the dfi dt is negative 2 dissipation function. So this dissipation function characterizes the rate of this energy lost when the system against the fractional force. So that is work done by system or system lost energy. So I just give that one. Now we discuss the Okay, that is one example here. Give this non-conserved force. Now we are going to discuss the feature of Lagrangian and Lagrange equations. Equation of motion. Okay, first, L is not constant even the energy is constant. That means for the system is conserved, energy is conserved. So this is always constant. But the Lagrange is not, because Lagrange is minus, right? It's kinetic minus potential energy. Then from here, kinetic energy is a constant minus potential energy. So that is like a constant minus 2V, right? Even though this is constant, but this V still change. We know for the conserved system, kinetic energy and potential energy always, if kinetic energy decrease, potential energy increase, or kinetic energy increase, potential decrease, keep the total energy is constant. So that is keep in mind that this is a developed feature for the Lagrange. Second one, L is not unique for this Lagrange equation. Okay, not this is one homework. The first problem I asked to prove. Not unique resulting that is, so what that means, if we have L prime, which is, let me see, right now is detail. So we know the function of general coordinates, general velocity, T, that equal to, if we know the Lagrange, but we build up new Lagrange, which is add a function of this. So what that means, here is the Lagrange we construct. If we add any total differential function, I'm going to explain this one, then we have a new Lagrange. This one means if the Lagrange satisfies the Lagrange equation, let's just now we consider all the conserved force. Then we build up new Lagrange L prime also satisfy this. So that is the meaning of this. Now here, the key is F to be a function of only general coordinates, not the velocity. Yeah. That is the key. So I would like you to, and this is total time dt. Okay, so if F is this, then total time dt is function of the general coordinates and general velocity, right? So here, G from 1 to n, partial F, partial Qg, and Qg dot plus partial F, partial T, right? That is the total time dt. So that is function of Qg and Qg dot and T. Homework. First one, D8. Let's ask you to prove this. So I leave this for you to prove that if we add any function which is, we didn't get any, it will restrict on the form of the function f, but if the f is only a function of general coordinates, not general velocity, then any function, it will hold true. The Lagrange equation still holds. So that is the feature. And the third feature is here, Lagrange function of general coordinates. Suppose we have two sets of general coordinates. You can select a Cartesian or select the spherical. Fine. As I said, the Lagrange will change its expression, but the Lagrange equation will not change. So that means the Lagrange equation is invariant under the different side of this general coordinates in Lagrange. Is invariant. And the transformation from one to another. So this transformation is called point transformation of the general coordinate. Say we have two sets of general coordinate, Qj and Sj. So that means the QJ is, if we say the point transformation means the S for each Si is a function of Qj. American I from 1 to n. So for each one we have a function, like transformation function. So then d dt partial L, which is a function Qj, function S J S I so J dot T partial S J dot minus partial L partial S J, which is function of S J dot P is equal to, if the Lagrange equation, Lagrange is a function of general coordinate Qj. So that means if we transfer from one side of the coordinate, a general coordinate, to another one, it will not change the Lagrange equation. And this is your homework. Second problem you are going to ask her to do. Okay, so that is the feature. Let's see. Good, we have time. Now we are going to apply this Lagrange equation or Lagrange formula. Now let's discuss how to apply. So here we derive Lagrange equation. We know to solve the equation motion of system, what we need to do is solve the Lagrange equation, right? So now here we are going to apply our application of Lagrangian formula. Formulation. First, condition. Which condition we can apply? The system needs which kind of system we can apply. If you remember, we go back to when we derived this or introduced the principle of virtual work, we have this constraint, right? So first, the condition. Okay. First one, we restrict. Remember, we restrict the constraint force due to the constraint due to the virtual work is 0, right? If not, we cannot apply. So you need to first double check. Even though we do not know the force, express the force due to the constraint, but we know the effect. So we can analyze that, the first. Second one, and when we want to solve the difficulty in solving the equation motion from Newtonian formula, we need two difficulties. One is the Ri, they are not independent of each other. So we introduce this general coordinates. And when we introduce general coordinates, if you remember, we need a condition. The constraints be holonomic. If your constraint is a holonomic constraint. If not, we cannot apply. That means we can write the formula, equation of constraint equal to 0. Alpha, how many? And we have a k, right? That is second condition you are going to judge yourself. And the third one, of course, this third one is usually for the non-conserved pose, it is a particular case, but in most cases, when we apply, we have 0 equation, right? So here, let's say for this one, if we apply the Lagrange equation, which we most cases we use, which is equal to 0, that is only for applied force is conserved force, right? That is another conditions before we apply is we judge ourselves. So if these three conditions satisfy, okay, we can apply. So this is a condition. Then once we have condition, let's look advantage of Lagrange equation. To compare with, or analytical mechanics compare with the Newtonian mechanics. So that is at the beginning of the class I mentioned. Sorry. Newtonian mechanics. Let's compare both, right? So this is analytical mechanics. We are going to summarize and see the difference and the advantage. So for the Newtonian, we are going to solve this equation of motion for the dynamics of the linear momentum. Analyze is force, right? Net force. So the net force include applied and plus the constraint, right? Constraint. Here, in this case, we will not do any, or this is equation of motion for this, if we apply the Newtonian mechanics. Equation of motion for analytical mechanics, this is the formula. G. So if I write down more general, include the conserved force and non-conserved force. We have 0. 0 is for conservative force. Conservative force. And non-zero if I use QJ prime, right? Include non-conservative. That is the formula. So here, I from 1 to n, right? We have n. So this GL from 1 to n. So you can see this equation of motion in both cases. If you compare both, what's the difference? Can I erase this part? Okay, this. So first, this is vector, right? So you deal with the vector analysis. You need vector analysis since we need to analyze the force. Force are vector. You have to carefully to analyze each individual vector of force and to set up the coordinates, project the vector force, each force, the x component, y component, z component. So that is very complicated vector analysis. Here, what do you need? You just need to find the total kinetic energy and total potential energy. That is scalar, right? Which one is easier? Scalar analysis, right? Because scalar analysis, we just find the kinetic energy, potential energy, and you don't need to care about this direction. This you should be careful deal with the direction. So that makes the formula, at least your analysis make this difficult. Okay. One. Here. Second, how many equations here? I from 1 to n, right? And this is a vector, so we have 3 components, so that we have 3 n equations, right? How many here? Lower n, right? So we have only n equations. That much more reduce the number of equations, right? Okay. And the third one. This one, even though in principle we can do, but it's very difficult to deal with the constraint, the force due to the constraint. If we cannot write this one, we cannot go further, right? So the difficulties is due to the constraint, right? Because it exists this, so that makes it difficult. But here, where the constraint of force? Get rid, right? So here we just, all the constraint, yes, we didn't ignore the constraint, but we do not include the force due to the constraint in the formula. All the constraint are included in where? Included in the equation of constraint, right? So this equation we can write as we have do some of examples. Here, this equation, right? So then make this doable, right? If here, impossible almost, if we cannot write down the force due to constraint, but here we can do. So that is the advantage of this Lagrange equation. Now let's go to how to apply. Let's give it a strategy or step by step. Then once, if we have time, we can do one of example. If not, at least I give you the strategy how to solve the problem, apply the Lagrange equation. So strategy. Of solving the Lagrange equation. Okay. First, analyze the constraint, right? That is the most important. We need analyze the type of constraint. Analyze the constraint. So, is holonomic or not? First, we need to know this. If yes, then you can have this write down. Okay, so now, if yes, write down the equations of constraint. That means you're going to write down here first. From 1 to how many constraints, right? So you have that the first analyze constraint, and if it is holonomic, write down this. So that is first step. Second one, okay. The degree of freedom, right? Degrees of freedom. That is n, right? N equal to 3m minus k. So once we have k, we know how many particles in the system, so you just very simply can determine this one. So the third one, choose the general coordinates. This one is depend on the experience. Which one you are going to select? you know I need to select 3. For example, the degree of freedom lower end is 3. Now I'm going to select 3. General coordinate, which 3 you are going to select? That depends on system and depends on your experience. And now we need to build up this one for the different system, right? We are going down. So now, once we have that, we are going to write down the transformation equation, the relation between the general coordinate and the position, right? Write down the transformation equations. That is, find the Ri is a function of general coordinates, and maybe time, maybe depend on time explicitly or implicitly. And then calculate the step 4. Now write down this and calculate Ri dot, which is a function of Qj dot. Why we are going to calculate this? Because we are going to write down the Lagrangian. Lagrangian, we need kinetic energy. Kinetic energy is a function of the Ri dot, right? So you need write down here, then all the Ri and Ri dot, the function of the general coordinates, general velocity. Then we can go to the next step. Step 5. We almost ready, so now we are going to write down is number 5. Write down the kinetic energy and the potential energy. So kinetic energy here, P is, this is a definition, right? That is why we need Ri dot. Once you have this, then you can substitute into this formula here. As I also mentioned before, kinetic energy, when you write down this way, or you can write down this, or this one, right? Depending on which system you prefer to write down in terms of center of mass and the relative kinetic energy, or just sum over all each individual. That's depending on system, right? So once you write down here, okay, write down here and potential energy. Potential energy is if you have external potential, Vi external plus this is just emphasize here is a function of the position and half of I from 1 to n, G not equal to I, V and G. You have a question? Okay, and this is also a function of Ri, right, for G. So first you write down, do not replace it by the general coordinates. This is a real position, right? This is a real position, real velocity. So when you write down here, then you are going to convert T and the U in terms of general coordinates and general velocity. That is, you are going to substitute this into your kinetic energy and potential energy. Then you have this kinetic energy is a function of, now is a function of general coordinates, general velocity, and your potential is also a function of, let me use general, maybe only function general coordinates, but sometimes maybe also include this. So that is, you are going to first write down correctly the energy, kinetic energy, potential, then you are going to substitute Ri and Ri dot into here. Then your kinetic energy and potential energy is a function of general coordinates. Now you can go to the build up the Lagrange, right? 7. Write down. Yeah. So L is T minus V which is a function of general coordinates, general velocity, and t. Now, once we have this, the remaining part became a mass. So for here, physics, and convert from these real coordinates to the general coordinates. Then now, number 7, number 8, okay. So now is mass calculate partial L, partial QG, partial L, partial QG dot, G from 1 to N. Since we are going to substitute into Lagrange equation, right? Then finally, number 9, apply Lagrange equation. So you're going to substitute here partial L, partial QG dot minus partial L, partial QG. Okay, equal to capital QG. Let's consider general case, general force, right? As I say here, it may be equal to 0. The conservative force, conservative, or equal to negative partial the dissipation function, partial QG dot. This is the dissipation function for the fractional force. You only have a fractional force as a non-conservative force, or others depend on system. No. Conservative. So that's the depend. You are going to apply this. All right, then the remaining, the others are solved. Okay, very good. Let me go to one example. So I think, I hope this example can help you for this qualified example. Here. Example 1 first. We just ask us find the lines force of particle. Okay. Moving in a plan. 2 dimension, right? Then, and so find one is this one, and second equation of motion. That means solve this equation motion of particle. So now first, let's set up xy coordinates. So this particle here is a mass, and x and y as coordinates. So now here, that is distance, that is y. Okay, just give a picture here. So we have applied force. This force we do not know, but ask her to find the general force associated with applied force, right? So now first analysis. Do we have a constraint? Oh, maybe you may say, okay, this is working on the 2D, so there's a constraint on 3D. Yes, that is one of constraints. You just work on this table, right? Or if we just consider the system in 2D, no constraint, right? You may say no constraint. Why? Yes, if no constraint is also applied, I mean the Lagrange equation, of course it works, right? So then it's no constraint, and then if no constraint, no equation of constraint, so no the function of FR. Now, then the, what is the K, how much? No, right? Number of equation for constant 0. So then, the degree of freedom n equal to, now I'm going to say it's 2n, since this 2 is 2D, right? Since we only consider 2D. Minus K, and n equal to 1, right? Only one particle. So that is 2 mod 1 minus 0 is 2. We need 2 degree freedom of the coordinates or general coordinate to characterize. Okay, so now we analyze. Now, choose general coordinates. We have to select 2. Which one you prefer to select? You can either we select x, y, or we use the polar coordinates r and phi. I'm going to use r and phi because they ask us general force. So you will see if we use this one, it gives us the force has a physical meaning, right? Or can correspond to something. So that is we select, then we select this one, right? Okay. If you select now, write down the transformational equation, right? So tools, I will not write, if you want to write down number 1, and 2, 3, and 4, the transformation equation is x, position x components, in terms of the general coordinates r and phi, we know that is r cosine, right? So that is a very easily find relation. And y is r sine phi. Good. So we quickly, because this case is simple, so we write down this equation of this transformation equation. Then we are going to calculate x dot, since we are going to determine the kinetic energy. We need x dot. Now here we do the direct, this implicitly depend on time, this also, right, when we do. So we have first, you want to do r dot, keep this constant, cosine phi, and then do this constant, this one. So we have a minus r sine phi dot, right? That is r x dot, and y dot is r dot sine phi plus r cosine phi dot. Okay, so once we have this, we are going to write down this kinetic energy here. Go to step 5. Okay. So step 5, let me see which I use this. Okay. Kinetic energy, since only one particle, easily that is m v squared, right? So that is half of m x dot squared plus y dot squared. Then you just substitute this together. The intermediate step I will not write. I think this is very familiar for you. Is r dot squared plus r squared y dot squared, right? You just substitute you will see you got this one. And that is nothing but in this polar coordinates, that is the kinetic energy. Okay. Now the potential energy. Potential energy, we consider this in the plane. So this plane is horizontal to the Earth. So the potential, if you select the plane 0, the potential 0. If you select the others, it's a constant, right? So whatever, just constant. It will not affect us. Okay. So that is. Then when we have this, you see we already directly convert from this partition, from this real position and velocity to this generate velocity, generate the coordinates, right? So now we go to next step. Since they asked the force first, right? So now let's first work on this and then we go to Lagrange. What is generalized force? By definition, okay, that is applied force, right? Applied, not constant force. Applied force, in this case, so we have actually just, since only one particle, right? Partial r. We don't need ri, partial r, partial qj, right? j from 1 to 2, that means qj either r or theta, r or phi. So by this, because this, so now there are two folds, right? Two general folds. One when the qj select r, another qj select phi. So let's first, let's do this. For qj equal to r, then this I'm going to use index capital QR, which qj equal to r, so that is f apply partial r, the inner product here, right? Partial r, right? qj is r. Did you follow me? Okay. So now here, partial r hat, r vector partial r, that is what? Is 1, but okay. Apply partial r hat, unit vector, right? R vector is r. This one, partial r, right? So this is 1. So that is the force, inner product, applied force is inner product r hat. What is? That is the force along the r direction, right? Whatever we have applied force, but the applied force this is the central force, right? So there's a point to the center of this, the origin of this position. So that is the central force. That means the applied force, whatever it has, which direction, but the project to the r direction, that play the role like this. Now for second one, qj is angle. Then the general force corresponds to this one. I'm going to use capital Q phi. That is applied force by definition. Inner product partial r, since I use this one, partial phi, right? R vector is r multiply r unit vector, right? And this one you must be careful here. Let me write down here. Okay, it's the force I still keep here because this one is partial. This one is this and the partial r hat with this. So two terms. And inside this term is partial r, partial phi. Keep the r hat, and the second one keep r, partial r hat, partial. The details, I think you go to math. This is a spherical polar coordinates, and then I just give you a result. So, and you can have questions on this one. This term keep. This one is 0 because r independent of phi, right? These two are general coordinates. They are independent, so this term is 0. Only second term. So that is inner product r, partial r hat, partial phi, and this one is nothing but this unit vector of phi, right? So phi is which direction? This is r hat, right? This is r hat, and we have. So now we have another force, which is has a. So this one is. This is a distance, right? This is nothing but torque. To this end. It's a torque. And that makes sense. The force perpendicular to this radial is make the rotation of particle. So that is once we know the force, then we can know when we select r and phi as general coordinates, this force can be coupled into two parts. One is just played as a center force, another played as a torque. So that is the answer to the first question. But I want to give you the second one to do this. Right? The second one, this is equation of motion, but I'm going to quickly. So equation of motion here, be careful here, the force is non-zero, and we do not know. So we cannot use here. That depends on either R and phi by, but we do not know the details, right? So we cannot do that. But if you remember, at the beginning we derived from the D'Alembert equation is partial kinetic energy, partial QG dot, minus partial kinetic and partial QG. That is this one. I actually think if you use this one, it's also okay, but assume we have the two terms, right? So if you use L over T, because L here, this is a constant. Since L equal to T minus A equal to T minus constant, so that's fine. So now let's do that. We're going to first partial T, partial QG, right? T is where? T is here. So we have two terms, partial T, partial R, dot. R dot, right? Here, R dot is one. Two cancels, so M R dot. And the partial T, okay, let's do the partial phi dot. Is this one. So that is M R squared phi dot. Then partial T, partial QG, we have also two terms. First one is partial T, partial R. Here, R is this term. We have factor 2 cancels, so M R phi dot. Partial T, partial phi is 0, since no phi, it's only phi dot, right? So when they have this, we have the solution of equation of motion, then the d dt partial T partial QG dot minus partial T partial QG equal to QG, right? So the G and this QG equal to R, then here. This one total time dt, so M R double dot, right? And this one is this one, right? Minus M R dot phi, sorry, R dot phi equal to F R, right? QG equal to phi is this term, and this term, be careful, we have this depend on time, this depend on time, so we have M, sorry. D this term, right? Total time dt, so that is 2 M R dot phi dot minus M R squared phi double dot equal to I think I have a minus, oh. If I have this one correct, this one is correct. I have a sign here, partial. This is not, sorry. Yeah, this term is 2 times, right? Okay. That's now, sorry.
Hi, sorry,
Yeah.
I don't mean to interrupt, but does somebody in here just get off of a TARC bus by chance? Did this class just start?
You mean this?
Yeah.
Yeah.
Sorry, I have an AirTag in my wallet, and I lost my wallet on a TARC bus, and so I've been tracking it down. So now I'm just going around asking people if anybody's found it.
Who can
No one, no idea? All right.
No idea.
Stop right out this window.
I don't stop at this TARC stop.
All right, so
It is on the wall.
just occupy the 7 minutes. I hope this can help. If you have this type of problem in the exam, I hope that can help you to analyze. The key is to find this general coordinate, and then you just do step by step. You will come, and then go to the further examples next Tuesday. Good luck. Yeah, do your best. Sure.
Yeah, the black double doors.
You can erase now.
Okay.
All right, now come in.